Hello, in this lecture we find out the length of line segment AE. In the drawing we have rectangle ABCD. We know that side AD of this rectangle is equal to 3 units in its length. In addition, inside this rectangle we have those two semicircles. The radius of this big semicircle equals to 2 units in its length. The radius of this small semicircle is equal to 1 unit in its length. And again, our mission was to find out the length of this line segment AE. So first of all, we know that all those four angles inside rectangle ABCD are right angles. So I write it down. So actually, this is a right angle. This is also a right angle. This is a right angle. And finally, this is also a right angle. In the next step, we will define the relevant points for this question with letters. We will define the center of this big semicircle, this point as point P. We will define the center of this small semicircle, this point as point Q. We will define the touching point of those two semicircles, this point as point S. We will define the point of tendency of tangent AE with this big semicircle, this point is point L. And finally, we will define the point of tendency of tangent AE with this small semicircle, this point is point G. In the next step, we will do a construction. That is to say, we will extend side CD and line segment AE by a straight line until they touch each other. So actually, this is their touching point. We define their touching point, this point is point F. DC is one side of this rectangle ABCD. Therefore, it is absolutely a straight line. Okay? And we extended the straight line DC by a straight line, and therefore the result must be a straight line. So the result DF must be also a straight line. If you focus on the upper side of this straight line DF at point C, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of DC at point C? We have this angle that is equal to 90 degrees plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So this is a right angle according to rule 3. We will define the size of this angle EFC as alpha. So inside the small right triangle ECF, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees it is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, in the big right angle ADF, in this big right angle ADF, this angle equals to alpha. This angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus alpha. According to the symbol, the sum of the angles in any triangle is equal to 180 degrees. Okay. PL is the radius of this big semicircle that is equal to 2 units in its length. The radius PL is drawn to point L, that is the point of tendency of tangent AE with this big semicircle. So now we can implement it all one. According to all one, the tangent to the circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have a circle, and we have also tangent AEB, that is tangent to this circle at this point M. We also have here the radius OM that is equal to R, the radius OM that is equal to R is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule, all one. So we can actually implement all one in our drawing. One, because in our drawing, we have the radius PL of this big semicircle is drawn to point L, that is the point of tendency of tangent AE with this big semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AE will be perpendicular to the radius LP. If AE is perpendicular to LP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we have the radius QG of this small semicircle, the radius QG that equals to 1 is drawn to point G, that is the point of tendency of tangent AE with this small semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent QG will be perpendicular to the radius AE. If QG is perpendicular to AE, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, all one. So in this small right angle GQF, this small right angle GQF, this angle equals to alpha, this angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus alpha. Likewise, in a big right angle LPF, this angle equals to alpha, this angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus alpha according to the symbol that says that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we will prove that the right big triangle LPF, this right big right triangle LPF is similar to this small right triangle GQF. Okay, so I write it down. We prove that the big right triangle LPF is similar to the small right triangle GQF. So why those two right triangles are similar to each other? First of all, those two angles, they are both equal to 90 degrees and therefore they are equal to each other. So actually, this is angle PLF. In the big right triangle LPF, and it is equal to this angle, that is actually angle QGF. In the small right triangle FGQ. Work it again. I can found out that angle PLF in the big right triangle LPF equals to angle QGF in the small right triangle FGQ. They are both equal to 90 degrees and therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles. So I can write down that angle alpha equals to itself as a common angle that belongs to both triangles. So if we relate to this angle alpha as it belongs to the big triangle LPF, it will be defined as angle LFP. And angle alpha equals to itself. So if we relate to this angle alpha as it belongs to the small right triangle GQF, it will be defined as angle GFQ. Again, this equation means that angle alpha equals to itself. We just call to angle alpha two different names. Angle alpha equals to itself as a common angle that belongs to both triangles. And finally, those two angles, they are both equal to 90 degrees minus alpha, and therefore they are equal to each other. So actually, this is angle LPF. In the big right triangle PLF, and it is equal to this angle, it is actually angle GQF. In the small right triangle FGQ. So repeat again, we actually found out that angle LPF in the big right triangle PLF equals to angle GQF in the small right triangle FGQ. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we actually proved that all the figures of this big right triangle LPF are correspondingly equal to all the figures of this small right triangle GQF. Therefore those two right triangles are similar to each other according to angle similarity rule. So write it down. So the big right triangle LPF is similar. This is the sign of similar to the small right triangle GQF according to angle similarity rule. And from the fact that the two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We derive that side LP in the big right triangle LPF over side GQ in the small right triangle FGQ is equals to side PF in the big right triangle LPF over side QF in the small right triangle GFQ. So repeat again. We divide that side LP in the big triangle over side GQ in the small triangle equals to side PF in the big triangle over side QF in the small triangle. LP is the radius of the big semicircle that is equals to 2 units in its length over GQ. GQ is the radius of this small semicircle that is equal to 1 unit in its length, and it is equals to PF. What is the length of PF? First of all, we know that PD equals to PS, they are both the radii of this semicircle, that is equal to 2. So PD equals to 2 units in its length, and PS also equals to 2 units in its length. Likewise, QS equals to QC equals to 1. They are both the radii of this circle, that is equals to 1. So QS equals to 1, QC also equals to 1, and finally we define the length of this line segment CF as x. Again, CF equals to x according to our definition. So in total, the length of this line segment PF will be equal to 2 plus 1, that is 4, plus x. Again, in total, PF equals to 2 plus 1, that is 4, plus x. So PF in total equals to 4 plus x. Divided by QF. QF equals to 1 plus x. Again, QF in total equals to 1 plus x. So in conclusion, we found out that 2 equals to 4 plus x over 1 plus x. Here we multiply this equation by 1 plus x, and we get that 2 times 1 plus x equals to 4 plus x. Here we open the brackets on this side of the equation, and we get that 2 times 1 is 2, plus 2x equals to 4 plus x. Here we subtract x from this equation, and we get that 2x plus x is x, so in total, in this side of the equation, we have x plus 2 equals to 4. Here we subtract 2 from this equation, and finally get that x equals to 4 minus 2, that is 2. So actually found out that the length of line segment x is 2 units. Here, according to our definition, CF equals to x, and x equals to 2 units in its length. In the next step, we will prove that the biggest triangle in this domain, that is triangle ADF, is similar to the smallest right triangle in this domain, that is triangle ECF. Okay, again, we will prove that the biggest right triangle ADF is similar to the smallest triangle ECF. So as now, we will prove that the big right triangle, or the biggest right triangle ADF, is similar to the smallest right triangle ECF. So why the biggest right triangle ADF is similar to the smallest right triangle ECF? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So actually this is angle ADF, the biggest right triangle ADF, and it is equals to this angle, that is actually angle ECF, as well as right triangle ECF. So I repeat again, actually found out that angle ADF, the big right triangle ADF, equals to angle ECF in the small right triangle ECF. They are both equal to 90 degrees and therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles. So we can write down that angle alpha equals to itself as a common angle that belongs to both triangles. If we relate to this angle alpha, as it belongs to the big right triangle ADF, it will be defined as angle AFD. And angle alpha equals to itself. So if we relate to this angle alpha, as it belongs to the small right triangle ECF, it will be defined as angle EFC. So again, this equation means that angle alpha equals to itself. We just call to angle alpha two different names. Angle alpha equals to itself, it's a common angle that belongs to both triangles. And finally, those two angles, they are both equal to 90 degrees from alpha, therefore they are equal to each other. So okay, this is angle LPF. In the big right triangle, no, I made a mistake. Here actually, those two angles, they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So okay, this is angle FAD. In the big right triangle AFD, and it is equal to this angle, that is actually angle FEC. In the small right triangle EFC. So I'll repeat again. Actually found out that angle FAD, the biggest right triangle AFD, equals to angle EFC in the small right triangle ECF. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So if we found out that all the fingers in the big right triangle ADF are correspondingly equal to all the fingers in this small right triangle ECF. And therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. Actually found out that the big right triangle ADF is similar, this is the sign of similar to the small right triangle ECF according to angle similarity rule. And from the fact that the biggest right triangle AFD is similar to the smallest right triangle ECF, we derive that the following relationship exists between their sides. We derive side AD, the big right triangle ADF, over side EC in the small right triangle ECF, equals to side DF in the big right triangle ADF, over side CF in the small right triangle ECF. So I repeat again, we will derive that side AD in the big triangle over side EC in the small triangle equals to side DF in the big triangle over side CF in the small triangle. AD equals to 3 units in its length according to what is given as the question. Or over EC. EC is the missing side, so we leave it as it is. And it is equals to DF. What is the length of DF? DF in total will be equal to 2 plus 2 plus 2, that is 6, plus 1 plus 1, that is in total 8. So DF in total equals to 8 units. Over CF. CF equals to 2. So in conclusion, we have found out that 3 over EC equals to 8 over 2. 8 over 2 is 4, so I write it down. So we have found out that 3 over EC equals to 4. Here we multiply this equation by EC, and we get that 3 equals to 4 times EC. Here we divide this equation by 4, and finally we get that the missing side EC equals to either 3/4 or 0.75. Okay, so I write it down. Actually found out that this missing side EC is equals to either 3/4 or 0.75. What is the length of side BC of triangle ABCD? Again, what is the length of side BC of a rectangle ABCD? We know that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AD must be equal to the opposite side BC, but AD is 3, therefore BC must be also equal to 3. So I write it down. If we found out that BC equals to 3 units in its length, what is the length of the missing line segment BE? From the drawing, it is very easy to see that the BE equals to BC minus EC. Again, BC minus EC equals to BE. So I write it down. If we found out that BE equals to BC minus EC. So BE equals to BC. BC is 3 minus EC. EC is 0.75. So in total, if we found out that BE equals to 3 minus 2.75, or BE equals to 3 minus 0.75 is 2.25. So in conclusion, we found out that the missing line segment BE is equals to 2.25 units in its length. According to the same rule that the opposite sides of a rectangle are equal to each other, we get that side in rectangle ABCD, side DC must be equal to the opposite side AB. What is the length of side DC? From the drawing, it is very easy to see that DC in total equals to 2 plus 2, that is 4, plus 1 plus 1, that is in total 6. So in total, DC equals to 6, therefore the opposite side AB must be also equal to 6. In the next step, I'll copy the right green triangle ABE, this right green triangle ABE in a new page, and we'll implement the Pythagoras theorem on this right green triangle ABE. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the abbreviation for Pythagoras theorem. Again, side AB equals to 6 units in its length, side B equals to 2.25 units in its length, and the length of the hypotenuse AE is unknown. AE is the missing side. AE is the line segment that we're looking for in this question. Secondly, this is the right green triangle ABE that they copied from the original drawing. This right triangle ABE, according to the Pythagoras theorem, AE squared, that is the square of the hypotenuse, equals to AB squared plus BE squared. The hypotenuse AE is the missing side, so we'll leave it as it is. AE squared equals to AB squared. AB is 6, therefore AB squared is 6 squared, that is 36, plus BE squared. BE is 2.25, therefore BE squared is 2.25, that is equals to 5.0625. So in conclusion, we have found out that AE squared equals to 36 plus 5.0625. 36 plus 5.0625 is equals to 41.0625. Here we take a root out of this equation and finding that the missing line segment or the missing hypotenuse AE is equals to the square root of 41.0625. That is actually equals to 4.608 units in its length. I repeat again, I have found out that the length of line segment AE is equals to 4.608 units. So in the next step, I will summarize the lecture. In this lecture, we found out the length of this line segment AE. So in the drawing, we have rectangle ABCD. We know that side AD of this rectangle equals to 3 units length. In addition, we know that inside this rectangle, we have those two semicircles. The radius of this big semicircle equals to 2 units, the radius of this small semicircle equals to 1 unit. Again, our mission is to find out the length of this line segment AE. So first of all, we know that all the angles inside any rectangle are right angles. Therefore, all those 4 angles are right angles. In the next step, we define the relevant point to this question with letters. We define the center of this big semicircle, this point is point P. We define the center of this small semicircle, this point is point Q. We define the touching point of those 2 semicircles, this point is point S. And we define the point of tendency of tangent AE with this big semicircle, this point is point L. Likewise, we define the point of tendency of tangent AE with this small semicircle, this point is point G. In the next step, we did a construction, that is to say we extended side DC and line segment AE by side line until they touch each other. This is their touching point. We define their touching point, this point is point F. DC is one side of rectangle ABCD, therefore it is absolutely a straight line. Then we extended the side line DC by side line. When you extend a side line by side line, the result must be a side line. And therefore, the result DF must be also a straight line. So DF is a straight line. If you focus on the upper side of this straight line DF at point C, here the sum of the angles must be equal to 180 degrees according to the rule. Rule 3 that states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of DF at point C? We have this angle that is a right angle, plus this missing angle. In total, they must be equal to 180 degrees according to Rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So inside the small right triangle ECF, we define this angle EFC as alpha. So in the small right triangle ECF, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the right triangle ADF, the right big triangle ADF, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. From the sum rule, the sum of the angles in any triangle is equal to 180 degrees. We have, this is the radius PL. The radius PL of this big semicircle equals to 2 units in itself. The radius PL is drawn to point L, that is the point of tendency of tangent AE with this big semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AE will be perpendicular to the radius LP. If AE is perpendicular to LP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to Rule 1. Likewise, we have the radius QG of this small semicircle, the radius QG that equals to 1 is drawn to point G, that is the point of tendency of tangent AE with this small semicircle. And whenever you have radius that is drawn to the point of tendency, then tangent AE will be perpendicular to the radius QG. If AE is perpendicular to QG, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to the sum rule, Rule 1. So in this right triangle QGF, this angle equals to alpha, this angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus alpha. Likewise, in the big right triangle LPF, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha, according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we proved that this big right triangle NPF is similar to this small right triangle GQF. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, and therefore they are equal to each other. In addition, this is angle alpha, that is the common angle that belongs to both triangles. So we can write down that angle alpha equals to itself as a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, and therefore they are equal to each other. So we prove that all the three angles of this right triangle NPF are correspondingly equal to all those three angles of all the three angles of this small right triangle GQF. And therefore, those two right triangles are similar to each other according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side NP in the big right triangle NPF, or side GQ in the small right triangle GQF, equals to side PF in the big right triangle PF, or side QF in the small right triangle EFQ. So I repeat again, we derive that side NP in the big triangle over side GQ in the small triangle equals to side PF in the big triangle over side QF in the small triangle. LP is the radius of the big semicircle, that is 2, over GQ. GQ is 1. It is the radius of the small semicircle, that is equals to 1. And it is equals to PF. PF in total equals to 2 plus 1 plus 1, that is 4, plus x. Again, PF equals to 2 plus 1 plus 1, that is 4, plus x. So in total PF equals to 4 plus x over QF. QF in total equals to 1 plus x. So if we found out that 2 over 1 equals to 4 plus x over 1 plus x. Here we multiply this equation by 1 plus x and finally found out that 2 times 1 plus x equals to 4 plus x. Here we open the brackets on this side of the equation and finally found out that 2 times 1 is 2, so it is 2 plus 2x equals to 4 plus x. Here we subtracted x from this equation and finally found out that 2x plus x is x, so in total in this side of the equation we have x plus 2, that is equals to 4, so x plus 2 equals to 4. Here we subtracted 2 from this equation and finally found out that x equals to 4 minus 2, that is 2, so x equals to 2 units in its length. So okay, this is line 7 CF equals to x and x equals to 2, so CF equals to 2. In the next step, we prove the biggest right triangle in this domain, that is triangle ADF, is similar to the smallest right triangle in this domain, that is triangle ECF. So we prove that the big right triangle ADF is similar to this small right triangle ECF. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees and therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles, so we can write down that angle alpha equals to itself is a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees from alpha, therefore they are equal to each other. So we have proved that all the figures in the big right triangle ADF are correspondingly equal to all the figures in this small right triangle ECF. And therefore those two right triangles are similar to each other according to angle similarity rule. Okay, again, we found out that the big right triangle ADF is similar to the small right triangle ECF according to angle similarity rule. And from the fact that the biggest right triangle is similar to the smallest right triangle, we derive that the following relationship exists between their sides. We will derive that side AD in the big triangle or side EC in the small triangle equals to side DF in the big triangle or side CF in the small triangle. Then again, we derive that AD in the big triangle ADF over EC in the small right triangle ECF equals to side DF in the big right triangle ADF or side CF in the small right triangle ECF. AD is free over EC. EC is the missing side, so we leave it as it is. It is equals to DF. DF in total equals to 2 plus 2 plus 2, that is 6, plus 1 plus 1, in total is 8. So DF in total equals to 8 units in its length over CF. CF equals to 2. So we found out that 3 over EC equals to 8 over 2. 8 over 2 is 4. So in total we found out that 3 over EC equals to 4. Here we multiply this equation by EC and finally found out that 3 equals to 4 times EC. Here we divided this equation by 4 and finally found out that the missing side EC equals to either 3/4 or 0.75. And again, we should find out that this missing side EC equals to either 3/4 or 0.75. What is the length of side BC of rectangle ABCD? According to the rule that the opposite sides of a rectangle are equal to each other, we get that side AD must be equal to the opposite side BC. But AD is 3, therefore BC must be also equal to 3. Here, BC equals to 3. What is the length of the missing 9/7 BE? 9/7 BE equals to BC minus EC. Again, BC minus EC equals to B. Repeat again, BE equals to BC minus EC. So BE equals to BC, that is 3, minus EC, that is 0.75. So in total, BE equals to 3 minus 0.75, that is 2.25. Repeat again, the missing side, the missing 9/7 BE equals to 2.25 units in its length. According to the same rule that says that the opposite sides of a rectangle are equal to each other, we get that in rectangle ABCD, side AB must be equal to the opposite side DC. What is the length of side DC? DC in total equals to 2 plus 2, that is 4, plus 1 plus 1, that is 6 in total. So DC equals to 6, and therefore the opposite side AB must be also equal to 6. In the next step, I copied the right green triangle ABE in a new page, and we implemented the Pythagoras theorem in this right green triangle ABE. Okay, this is right green triangle ABE that is going to the original drawing. Here by PT's information for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in this right triangle is AE, therefore the square of the hypotenuse is AE square, and AE square must be equal to AB square plus BE square. AE is the missing side, so we leave it as it is, so AE square equals to AB square. AB is 6, therefore AB square is 6 squared, that is 36, plus BE square. BE is 2.25, therefore BE square is 2.25 square, that is 5.0625. So in total, we found out that AE square equals to 36 plus 5.0625. 36 plus 5.0625 equals to 41.0625. So in conclusion, we found out that AE square equals to 41.0625. Here we took out all of this equation and finally found out that the missing 9/7 AE equals to the square root of 41.0625. So AE equals to 4.608 units. Repeat again, we found out that the length of this 9/7 AE is equals to 4.608 units. Okay, thank you very much.